Welcome in Fraunhofer ISE's Digital Grid Lab. Today I want to present you how we test fast charging infrastructure with our PowerHIL infrastructure. But before we talk on e-mobility, I want to introduce you to our Digital Grid Lab, our PowerHIL lab. The central unit is our HIL system with several Typhoon HIL 604. And this can be extended with some power amplifiers to a PowerHIL system. We have chosen for the lab the Synergia of the type GEL, so they all have a rated power of 100 kilowatt, can operate in AC/DC and also in the grid emulation and a load emulation. And on the other side, because it's a digital grid lab, we have a commercial control center infrastructure it's called the PSE print software, and this can be connected via communication interfaces to the digital twin hosted on the HIL computer, and we can test smart grid controllers and so on. One application is the test of electric vehicle supply equipment. I want to show the general setup. When we want to test a DC fast charger, we can connect it to the public grid just to power it. Or in experiment, it could be also a grid emulator to emulate a weak grid. On the other side, we can use our HIL computer to model the charging part of the electric vehicle. Basically, that means we model the battery and the electric vehicle charge controller, the EVCC. For the real PowerHIL setup, we need to make a connection between HIL computer and the device under test. We call this the PowerHIL interface, which I will describe in the following. First part is a power amplifier, which is controlled by the HIL computer and emulates the battery. But we also need communication between charger and electric vehicle, which is mainly done via CP contact. The communication is established on two levels. On low-level communication, we have the pilot signal, as we know it from AC charging. For now, we just need to know this is a PWM signal. And the charger tells us with the duty cycle of pi 5% that it wants higher level communication. The high level communication is established with the modulated PLC communication on the CP contact. That means there's the Ethernet connection created between the electric vehicle and the charger. This communication is done by standard 15.11.8-2, and various messages are communicated. Let's have a look how the setup looks in the Digital Grid Lab and start with an overview. On the left, we see our power charger, the device under test. And on the right, in the cabinet, we have on top the HIL computer with its analog and digital in and outputs. And this is connected to the charging unit via our emulated car, and it starts here the connection with our CCS inlet, which makes basically the connection to the power amplifier on the bottom, and also connects the CP and PP contact and all the other contacts via the HIL Connect and via the board for the higher level communication, which is establishing the Ethernet communication for ISO 15118. When we focus on the CCS board, we can see how the CP and PP contact is linked to the analog inputs from the Typhoon HIL computer, and we can see various digital contacts which control the CP signal. And on the other hand, we see also the ISO 15118 modem, which is making the communication from the CP signal to the HIL interface of the computer. Now you have seen the whole setup, and before we plug the device under test, I want to say a few words on the model. The important unit to link this model to the emulated car is the CCS interface, where we basically have the analog inputs of the CP signal and of the PP signal. And we also link the AC connections, and in this case, we'll talk today, the DC connections, the measurements from the outside to the modeled battery. That's the main source for the charge controller, the EVCC. And here we most important make the control of the allowed charging current for the battery, all the other signaling things around the controller, and for now most important, the ISO 15118 communication is linked to the measurement. And the EVCC also is controlling our power unit, which is basically a model of a battery in combination with a converter to connect it to AC or to charge it also via DC, and for later there's a current source for emulating a driving demand. And finally, we have an interface for the user. We can have some settings and measurements for the user. After the model is compiled and loaded to the HIL computer, we can open our SCADA interface. We see here basically the user interface to the electric vehicle, and which we can control here the charging process with the set current and the interface to the CCS, locking and unlocking. We have various subpanels for the battery, for the electric vehicle charge controller, and for the electricity grid. And most important, we have the interface to the power amplifier, which is controlled via Modbus. Now you have seen all components that are important for the Power HIL setup. So now we can connect to our power amplifier. So we establish the Modbus communication, and with our start macro, we enable the charger. You can see on this camera on the top right, you can see a video from the power amplifier, the Synergia, and after, when the device is running, we should see here the running in the window. So now everything is set up for connecting the DC fast charger. Before we connect the hypercharger to our HIL setup, I'll have opened from the EVCC tab the subpanel of the ISO 15118 communication, and once the session is active, we can see here the current phases of the initialization and charging process. Let's plug in the supercharger, and we start also the supercharger. And then after a few seconds, you can see the session is active. We go to the charge parameter requests. Now we enter the cable check response. After the cable check is done, we should enter the pre-charging phase, and finally, via power delivery phase, the current demand phase. In the communication window, we can now see what is the maximum power the supercharger provides. In this case, it's up to 60 kilowatt and a maximum voltage of 500 volt and a maximum current of 140 amps. We see also our current voltage, and now I can set a current. Let's put a current of 50 amps. Then we can see the current is increasing, and if you observe also the window of the camera from the power amplifier, you can see the same voltage, 417 volt, and a current of overall a power of 20 kilowatt. Yeah, and we can do this. You can see in the user panel that the state of charge is increasing. I increase it a bit more. We go to 100 amp, and let's go. You can observe all the values, and let's go to the maximum, to 144. And then you sometimes can see that we are at the maximum the charger can provide. So sometimes we're at current limit or at the power limit. Now the charging process is going for a while. So we see we charge with 50 amps and the charging state of charge of 81%. And we compare our user interface with the camera focused on the display of our hypercharger we are testing. So basically you compare we have a charging current of 50 amps, and we can see the state of charge communicated via ISO 15118, and we can see that we already have charged 1 kilowatt hour in the last few minutes. Let's increase power a bit and reactivate the display, and I'll put it to 100 amps charging. So we see, as expected, a charging power of 40 kilowatt and an increasing state of charge, and very soon it should go to 82% also on the display. And after the communication is done, we see it here. And finally, one last example with the most maximum current, so with 140 amps, and you see our car should be charged in 8 minutes, and yeah, we have charged quite a few kilowatt hours. In the last minutes, I gave you an overview about the setup in our Digital Grid Lab, and if you have any questions, I'm happy to try to answer them now or later. Thank you very much.
Check the video description for more resources on this topic, including how to download and get started with Typhoon HIL Control Center for free. You can also visit HIL.academy to access free courses, expand your HIL testing skill set, and get certified. Subscribe to our channel to get notified about new content.